All right, here's our third and final video on probability. We'll talk about conditional probabilities and also independent and dependent events. Okay. By the end of this video, I hope you're able to answer questions that involve conditional probabilities. Okay, so what is a conditional probability? It is an event that will occur given that some other event occurs. Okay, the probability is written this way, which means the probability of B given that A is true. Okay, so n, example 1, if n is a randomly selected integer from 1 to 30, what is the probability that n is 5 given that it is less than 12? Okay, well, how many 5s are there? There's only one 5. Okay, and given that it's less than 12, I won't put 30 in here, but I'll put 11. Okay, so being less than 12, I don't include 12. So if I count from 1 to less than 12, I'm actually getting 11 numbers. And so 1 out of 11 is the probability. Okay, example 2, what is the probability that n is odd given that it is prime? We got to think through how many odd numbers there are. Let's see here. If n is odd given that it's prime, so we're looking at just the prime numbers. So the prime numbers between 1 and 30 are 2, because 1 actually isn't prime. That's a whole other topic, though. 2, 3, 5, 7, 11, 13, 17, 23, 29. And that should be it of all the prime numbers between 1 and 30. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's think about that as the sample space in these problems. Okay, how many of them are odd? There's 8 of them that are odd. So 8 out of 9 is the probability, given that the number is prime. Okay, before we jump into an actual formal formula, let's talk about what an independent event is. Two events are independent if one doesn't affect the other. Okay, for example, if a student is a female and a student being a senior shouldn't be independent events. A student being a female does not, change our guess that she's a senior or not. Those two events are theoretically independent. Now, if we're at a school and there's lots of seniors who are females and lots of underclassmen who are males, that may change our belief, but theoretically it shouldn't. Okay, and we'll learn how to look at two events and the probabilities and see if they are independent or not. Okay, dependent events are two events that are dependent if one occurring affects the other one occurring. Okay, a student taking an AP class and a student being on the honor roll are probably not dependent events. I'm sorry, they're probably dependent events. If a student is taking an AP class, that'll change your belief if that student's on the honor roll or not. Okay, so those are two dependent events because if you know that one occurs, it'll change your guess about the other occurring. Okay, now there's blanks here because I want you to pause the video for a second and to put down what an example that you can think of an independent or a dependent event. So something that two events that you think knowing one happening would not change your belief about the other happening, or for a dependent event where knowing one thing will change what you think about the other one. Okay, a reminder from the last video that if A and B are independent, the intersection of A and B is the probability of A times the probability of B. Okay, if they're dependent events, they're not independent, then it's similar, but the formula is like this: the probability of A times the probability of B, given that A is true. Okay, so here's an example. Find the probability of drawing the given cards from a deck of 52 cards with replacement and without replacement. Okay, so in A, I'm drawing a jack and then a queen. Now, with replacement, the probability of me first drawing a jack will be 1 out of 13. Okay? If I put it back in and then shuffle the cards and pick out a second card, the probability of it being a queen is also 1 out of 13. Okay? So you get 1 out of 169, which decimal might be easier for us to work with. 1 out of 169 is 0.0059. Okay, that's with replacement. Okay, B is without replacement. So if I pick up a jack and I leave it in my hand and pick up a new card, as we typically do in card games, 1 out of 13 times, let's see here. If I've already taken a card for my jack, and there's only 51 cards left, and how many of them are queens? There are 4 queens left. And so we have 4 out of 13 times 51 is 663. As a decimal, 4 out of 663 is 0.0060. Okay, so it changes slightly with or without replacement. Okay, now in A, if you're doing it with replacement, those two events are independent. So drawing a jack and then drawing a queen, those two are independent. If you're doing it without replacement, where you're keeping the card, you're looking at a conditional probability. So given that you drew a jack the first time, the probability of drawing a queen changes. Okay, example 4, a face card and then a 10. So in A, with replacement, drawing a face card, let's see here, there's 3 out of 13, because Jack, King, Queen are all face cards out of the 13 that are possible. And then if you put it back, and then drawing a 10 would be 1 out of 13. So the answer is 3 out of 169, which is about 0.0178. Okay. B, a face card and then a 10 without replacement, you would pick 3 out of 13 for the first card. But then the fact that you don't put it back changes your belief about the next card being a 10, because there's only 52 cards left. I'm sorry, 51 cards left. There are 4 10s left. And it's going to be equal to 12 out of 663, which is approximately equal to 0.0181. Okay. Okay, some more complicated problems with tree diagrams. Now these show up quite a bit in statistics. Okay, so make sure you understand how to do tree diagrams, because they're pretty important as we move along. Using observations made of drivers attending a certain high school. Drivers arriving at a certain high school. A study reports that 69% of adults wear seatbelts while driving. A high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt, and 26% of the time when the adult does not wear a seatbelt. What is the probability that a high school student in the school wears a seatbelt? Okay, so there's like things going on. There's a parent, sorry, an adult wearing a seatbelt or not, a student wearing a seatbelt or not, a lot of different things going on. A tree diagram is perfect for setting this up. So I'm going to have the first, this is thought of as a node, and I'll go here and here with whether or not the adult is wearing a seatbelt. So 0.69 is them wearing a seatbelt. So let me see, I'll say yes. Okay. And then 1 minus 0.69 is 0.31. There's a 31% chance that they're not wearing a seatbelt. Okay, now here's where conditional probability comes in. Given that the adult is wearing a seatbelt, the student will wear a seatbelt 66% of the time. Is 0.66. okay? Which means the adult is wearing it and the student is not wearing it is going to be 1 minus 0.66 or 0.34. Okay, now given that the adult is not wearing their seatbelt, a student will wear a seatbelt 0.26% of the time, which means the other 0.74% of the time they're not. Okay, now we can look at the probability of each, branch or leaf, if you want to call it that, is where, just like in this formula, we multiply them together. So you kind of multiply as you go through the tree. So this happening is 0.69 times 0.66. So 0.69 times 0.66 is 0.4554. Okay, so both the adult and the student, both wearing their seatbelt, is about 45% of the time, 46% of the time. Okay, a parent wearing the seatbelt and the student not wearing the seatbelt will happen 0.69 times 0.34, which is 0.2346. Okay. Now you could do that for each one. I'm only doing the ones that are useful to us, which, by the way, this one is not useful to us, but I wanted just to kind of show you how to do it. So these two cases where students are wearing seatbelts are the ones that are important for us in this problem. So this one is a student. So this is 0.31 times 0.26, and I get 0.0806. Oops. 0.0806. Okay, now these two events are, I'm looking at this or this happening, and in or situations, I always add them together. Okay, so this or this happening, I will add those two events together. Now there's no, these are two disjoint events. You can't have the adult wearing and not wearing the seatbelt. It's one or the other. So I'll just simply add them together. 0.4554 plus 0.0806, and I get 0.536 is the probability that a student is wearing a seatbelt. Okay, another example is drawing cards with a given, check two more examples. Okay, drawing a red card and then a king. Well, the reason why it's a little more complicated is because some kings are red cards. So the first node will be if it's a red card or not. So 0.5 and 0.5, this is if it's red or if it's black card. Okay, and then drawing a king, you know what? These are not tree diagram questions because if you drew a black, then you're done. If you drew a red card, and then a king, so it's not actually a, let's do it anyway. Our red card will be 0.5, and then the probability of drawing a king, okay, let me try again. There's a 50% chance of you drawing a red card, okay? Now, the next card being a king or not depends on what you drew the first time. So it being the red king, sorry, a red king, there's two red kings, and not drawing. Okay, now the probability of you drawing a red king would be, all right, I've got this one figured out now, but we're getting close to our 15-minute mark for YouTube, and so I'm going to cut off this video, and there'll be a part 2 for this video.